Okay, not Cy. All right, so summation about forces in the x direction is equal to 0. So you have minus dx minus 150 times 10 to the power 3 plus by 200 times 10 to the power 3 minus by 157 with 157.92 times 10 to the power 3. The whole thing is equal to 0. Okay, so dx. So I'm going to bring dx over. Dx will be equal to minus 150 power 3 plus by 200 power 3 minus by 157.92 power 3 is equal to minus 107.92 times 10 to the power 3. I'll do it again. So minus 150 power 3 plus 200 power 3 minus 157.92 power 3. So it's equal to minus. So therefore dx is equal to minus 107.92 times 10 to the power 3. So this is static analysis, right? So for it to be positive, the force has to be acting towards the right. So again, this initially we assume wrongly. And why this is the case? This is because of the internal load. Without the internal load, it has to still push what? Outwards. Okay. Now we are not done yet. So the question asks us determine the average stress in each section. Okay. So we are going to determine the average stress. Okay. So we are going to look at section number 1. So section number 1. Wait.
Sir.
Yes.
Question. Hewan has a really good point. Why did we choose CX instead of DX?
You can do either way.
Okay.
It will work.
Okay.
You can hold CX and remove DX. Your answer will be the same.
Okay.
Okay. that's a good one. Okay. So let's look at section number 1. Okay. So now we are going to find the stresses. I'm going to see yeah. So what I'm going to do is I'm going to copy this whole diagram again. Right. So we know that now we have our CX, which is equal to what? Which is equal to 157.92. Okay, 157. Okay, so the question asks us, we're going to find stresses. Okay, find stresses acting on DA, on AB, and on BC. Okay. And again, we apply the hangman theory. Okay, so section 1, right? We have our DA. So stress DA is equal. So the 150 is going to be in compression. The 200 is going to be in tension. And then we have a redundant load coming at 157.92. Okay, so the whole thing divide by cross-sectional area. So the cross-sectional area is wait, I'm a bit dazed now. The cross-sectional area is 1.963 times 10 to the power minus 3. Okay, so this will be equal to minus 150 power 3 plus 200 power 3 minus 157.92 power 3 divide 1.963 power minus 3. Okay, so it's minus, sorry, I always forget my minus down here. So it's equal to minus 54.977, okay, times 10 to the power 6 Pascal. Okay, then we look at section number 2. So that is our stress AB. So section number 2, we don't get to see the 150, but we get to see the 200. So the 200 is going to go into tensile mode. Then minus by 157.92. And then the cross-sectional area is 314.159 times 10 to the power 6, right? So this will be equal to 200 power 3 minus 157.92 power 3 divided by 314.159 power minus 6. Eugene, don't miss the minus sign. So this will be plus 133.945 times 10 to the power 6 Pascal. And then we have section 3. Okay, so you can see stress BC. So stress at BC, you only can feel the what? It can only feel the 157. Okay. That's why I taught the handbang last week. So now when you do this, oh no, the area is wrong. So the area is 1.963 times 10 to the power minus 3. Okay. So this will be equal to 157.92 power 3 divided by 1.963 power minus 3. So it's equal to 80. So it's minus 80.44 or 448 times 10 to the power 6 Pascal. Okay. Right. So I think I have some not spare time. There's no spare time in this course. What I'll do is there's a very good question. Why do we choose CX? Let's say now we do DX. Okay, so if we do DX, okay, so now I'm going to remove the load. Okay, so I'm going to remove the load. Okay, this is an alternate, okay, alternate solution or alternate solution. All right, so we are going to remove the load at point D now. Oh, so remove the load, remove the support. Okay. At point D. Okay. So when we remove the support at point D, so I'm going to copy the same thing. Okay, I'm going to do this. I'm going to copy. And then down here, I'm going to paste. And then I'm going to rotate right once, rotate right twice. Okay. I know it's a bit skewed, my bad. Okay, so what we're going to do now is we're going to remove the support at D now. Okay, so this is point D. We remove the support. Okay, so this is our point C, right? So this is our support. Okay, so we're going to do this now. Okay, so what you'll see different is some numbers will what? Will change. Okay, so we're going to see what is the number will change. Okay, so we are going to calculate now, right? Okay, so now we have the 200. So deflection of 0.3. will be equal to, so now we have minus 200 10 to the power 3 plus by 150 times 10 to the power 3. Then you have your length, which is equal to the length is equal to 0.25 divided by cross-sectional area is equal to, hold on, let me see what's my cross-sectional area. My cross-sectional area is 1.963 times 10 to the power minus 3. Young modulus is 101 times 10 to the power 9. Okay, so this will be equal to minus 200 power 3 plus 150 power 3 divided by 0.25 times 1.96. Wait. Minus 50 power 3 divided by 2.25 divided by 1.963 power minus 3 minus 101 power 9. So 200 power 3. Now my calculator is not behaving. No, it's the user. Okay, multiplied by 0.25 divided by 1.963 power minus 3 divided by 101 power 9. So it's equal to minus 63 point, minus 63.0. Okay, 63.0. Hold on. So 63.048 times 10 to the power minus 6 meters. Let me do it again. Minus 200 power 3 plus 150 power 3 times by 0.25 divided by 1.963 power minus 3 divided by 101 power 9. So it's equal to 63. Okay. So then we look at deflection at 0.2. All right. So deflection of 0.2, you will not see the 200, but you'll see the 150. So the 150 is going to be in tensile. So 150 times 10 to the power 3 multiplied by the length. The length is equal to 0.5 and divide by the area is 314.159 times 10 to the power minus 6, and then it's going to be on steel. So steel, we assume it to be how much? What was the steel value we used earlier? Steel, blah. I think we used 200, did we? Yep, 200 times 10 to the power 9. I'm not going to do all. We are just going to calculate the reaction at point D. Then I'm going to stop. Okay, we don't need to do the area. The area is going. The stress is going to be the same. So 150 power 3 times 0.5 divided by 314.159 power minus 6 divided by 200 power 9. So it's equal to 1.193 36 times 10 to the power minus 3 meters. Okay, let me do it again. 150 power 3 times 0.5 divided by 314.159 power minus 6 divided by 200 power 9. Yep. Okay, so then deflection of 1. So we know that this is equal to 0 because it's not going to feel any stresses. So the deflection due to the load will be equal to minus 63.048 times 10 to the power 6, right? And then we're going to plus by 1.1936 times 10 to the power minus 3, okay? So minus 63.048 power minus 6 plus a 1.1936 power minus 3. So it's equal to 1.13 055 times 10 to the power minus 3 meters. Okay, so 63.048 power minus 6 Eugene. Wakey. So minus 63.048 power minus 6 plus a 1.1936 power minus 3. So it's 1.13055. Okay, so now we go to our step 2. Now step 2, I'm just going to, because the expression, the geometry are still going to be the same, everything will be under compression. So for step 2, like what I mentioned before, right? So this whole thing, right? We are not going to see the load Okay, we're not going to see this load at all. Right, we're not going to see this load. Right, we're not going to see this load. Right, so now we have our reaction at point D. Okay, so reaction at point